All right, thank you very much, Dimitri. This is a huge pleasure to be here today to present Gaussian processes. This is what I've been doing for a few years now. And so the structure of this talk is going to be that I'm going to give you a very basic introduction to Gaussian processes. So the purpose really is to give you the basics. And then I will give you a lot of pointers to things that you may find useful if you want to dive more into certain topics in Gaussian processes. And first of all, I'm based at EURECOM. I was assistant professor at Glasgow before, at the University of Glasgow, and now I moved to and I'm assistant professor here at EURECOM. And just since Novi yesterday had a slide motivating, why you should go and visit him. Well, this is my way for you to, my way to motivate why you should probably think about visiting. So I'm based over here, okay? So this is a research center in a technological park in the French Riviera. And this is pretty much what happens every day, okay? This is really good. So so this is my 30-second slide on why you should come and visit, okay? Right, so these are my suggested readings for if you want to know more details about GPs. So there's this book online by Carl Rasmussen and Chris Williams, and you can download it online. They have an agreement with the publisher. I think it's MIT Press. And of course, a lot of the tools in Gaussian processes are based on probabilistic machine learning, and I think a good reference for that, at least personally, I think Bishop is a great place to find a lot of this material. Right, so this is the structure of this 1.5 hour presentation. So I'll start from some motivation, some examples, so that at least I'll show you some nice pictures at the beginning, and then, that's it. And then I'll give you an introduction to Gaussian processes, and there are, I think, two nice ways to, to present Gaussian processes. I'm not the only one that says that, of course. Even in Rasmussen's and Williams' book, you can find this distinction. And I really like to take these two different points of view to motivate and to try to understand what these Gaussian processes are. And I'll try to illustrate what are the challenges in modern machine learning to do, to be someone working on Gaussian processes these days, because everybody's doing deep learning these days, right? So what is the place of Gaussian processes within machine learning today? And this is a question I asked myself several times, and I also asked myself a few years ago when I decided to continue working in this field. And then I'll give you some pointers on what are really the latest developments on modern GPs. And of course, I mean, here we could talk about this for I don't know how many hours. If we went into the details of all these, like cool latest state-of-the-art techniques. I'll try to give you really the pointers and ways for you to navigate the literature. Okay. And by all means, feel free to interrupt me anytime you find something not clear. Okay. So I'll start with some motivation. So there is a fantastic paper in RSSB journal by Kennedy and O'Hagan, where they don't specifically talk about climate modeling, but I think this is a hot topic these days. So the idea is that you have a simulator that implements some very expensive physical process. Okay, so in this case, we're trying to simulate the weather in time and in space. Okay, so you can think of having lots of a very fine grid around the globe. Okay, a 3D grid, and you're trying to simulate the weather. Okay, so typically, you try to implement this by implementing the laws of physics, and there are several groups in the world that try to do this in several different ways. And if you run two simulators, you don't get the same result. And of course, if you observe data, not necessarily the predictions of the models match, right? So what you would like to do is to somehow account for the mismatch in the modeling of reality by using some statistical models. And perhaps also equip this with quantification of uncertainty, so that when you make a prediction, you don't just say, well, tomorrow is going to be at 12 o'clock is going to be 32.4 degrees, but you want to maybe have some notion of uncertainty on that. Okay? So when, in this paper, what they do, they try to combine the idea of Gaussian process modeling with simulations from physical systems. Okay, so equally, you can think of earthquake modeling and how important it is to be able to sort of alert the population when something like this is happening, especially if the earthquake is at sea, then we know that this can cause tsunami. So how do we quantify uncertainty, and how do we balance the cost of decision, of saying, alerting the population or not? Okay, so of course, decision theory is fundamentally embedded in, is built upon two pillars, which are the utility theory, that is, being able to assign a cost to a decision, and also probability theory that allows us to somehow get some belief about what is the probability of things happening. Okay, so here what I'm trying to say is that there are applications where quantification of uncertainty is important, okay? And I really liked yesterday's presentation, all of them, but specifically what Ray presented yesterday on non-parametrics, right? So why do we need non-parametrics? And well, in this case, you can think of, you would like to have something which is so flexible that is able to capture the mismatch between your physical model and reality, okay? So you would like something that potentially has infinite capacity, if you like, okay? Okay, so this is another application where I've been involved quite heavily in the last 5 years. So, if you have, scans, 3D scans of brains, it can be functional. You can measure the brain activity while people are doing some tasks, or, if you just measure the structure of the brain, then, you may want to have a way to say when people are healthy or need treatment. This is a really difficult problem because up to today, we haven't had so much data. So things are changing now. In the UK, they're collecting hundreds of thousands of images, okay? And they're tracking people over time. So soon we're going to be able to analyze huge amounts of data, which requires scalability, of course. And this is something I'll get to. But most importantly, what I would like to point out is that you really need some notion of uncertainty here to be able to say how uncertain my model is when it makes a prediction, yeah? Because giving treatment to people has a certain cost, not giving a treatment to people that are healthy, that need a treatment, then has another cost, potentially death. Okay, and neurodegenerative diseases in particular can have so many different time courses that you really would like to be able to not only be accurate at doing the diagnosis, but also knowing when you don't have enough information to do that, to make that decision. Okay. So this is another example. Imagine that you have, over time, okay, you have a number of accidents that happened throughout the years, okay? And, well, in this case, well, previously we talked about problems where we have a physical model, but in neurodegenerative disease, I don't have a way to say, well, what is the evolution of the brain structure over time when people have a disease or not, okay? So I cannot really write a physical model for that. And equally here, here you're trying to model what is the intensity of what is the rate of happening of these disasters in this coal mine. And you can, well, now forget about this for now, but what you would like to do is to be able to sort of do some count regression, if you like, okay? And here again, policies affect the way people work in mines and so on. So modeling all this is really hard, right? So you would like something which is flexible enough to be able to understand somehow this data, right? Model this data, explain this data. So, well, generally, this is another example. You have a bunch of data, you just want to do regression, maybe, okay? So, maybe you're interested in quantification of uncertainty for whatever reason, okay? So, maybe we need tools that are able not only to interpolate between the data. Imagine I generated this data from this function here with some noise, and I would like to have something that tells me what is the uncertainty around my predictions. Okay, so in general, this is what we would like to do. Okay, and not necessarily these labels are continuous, can be discrete, counts, whatever. Okay. So a model might be expensive to simulate. It can be inaccurate. So this is the case of climate modeling and earthquake modeling I gave you, but there are many, of course, many other examples. And maybe what we can do is to emulate the model itself, because if it's so expensive, maybe we cannot do any optimization of model parameters. So maybe we want to also have a surrogate for this model, or just have an emulation of the discrepancy between the model and reality, okay? And when we don't have a model, then we may want to replace it with something with a statistical model, okay, which is flexible enough, okay? So I'm not religious, of course. You know, if you tell me that you want to do this with deep nets, I'm happy with that, okay? But for the sake of today's talk, I'm going to present you Gaussian processes, okay? And again, the motivation, if you like, is based on the fact that these processes are non-parametric. So as the more data you get, the more the capacity of this model will grow, okay? So in deep nets, in general, you're going to have a huge capacity because you're modeling composition of functions. So generally, you know, this might be good enough. But the problem is that when is good enough? And optimization, you know, these days we do a lot of stochastic gradient optimization, which is really good for deep nets. Gaussian processes are kind of simpler in the formulation, a bit more elegant, if you like. So there is less parameter tuning to do. Okay, how many layers, what is the size of the layers, and so on. So I'm kind of drawn to these models for their elegancy, if you want, okay? Any questions so far? Okay, nothing spectacular, okay? So I told you that there are two ways that we can use to explain Gaussian processes, the weight space view and the function space view, and I'm gonna tell you a little bit about both. So in the weight space view, what you do is to think about Bayesian linear regression, okay? And the only thing you do is to make the number of basis functions grow to infinity, okay? So this is a very similar construction to kernel machines, okay? So I'm going to try to start from a Bayesian linear regression to give you a brief recap and then show you how you derive Gaussian processes from there, okay? So for the sake of notation, I like to color things, okay? So I like to color whatever we observe in orange, okay? Parameters in green, I didn't do it here because, well, it's a long story, but parameters here are W, okay? So for whenever we have a linear model, these are going to be black, but at some point, there are going to be some new parameters that are going to be green throughout the talk, okay? Okay, so when we do linear regression, what we think is that there is a linear combination of the features, okay? So XW, and then some noise that explains our observations, okay? So I call Y my observations, then X are the input, W and sigma square the parameters, okay? And here I'm assuming univariate output. It's easily extendable to multivariate output. So what people usually do is to put a Gaussian prior over model parameters. And now because the likelihood is Gaussian, okay, we can do a lot of cool things. So if you recall Bayes' rule, okay, so what we can do is to, if we're Bayesian, we want to characterize the uncertainty on the parameters given the data, right? So what we can do is to say, what is the posterior distribution over W given the observed data, X and Y, okay? So this is just the multiplication of the likelihood and the prior, okay? So this is the numerator of Bayes' rule, likelihood and the prior, multiplied together, and properly normalized, okay? So here I have all the bits and pieces. So posterior density is what we're interested in. And this is the distribution over parameters after observing the data. Then we have the likelihood, which is our measure of fitness, okay? So it's going to be higher if my W are good, okay? So this is what is the probability, if you like, of observing Y given the parameters. And the prior is anything we know about parameters before we see any data. So we can choose, you know, whatever covariance we want for these Gaussians over the parameters in the prior, and then the famous marginal likelihood in Bayes' theorem, which is just a normalization constant, okay? So we need to ensure that if we multiply two functions here, and this one integrates to 1, P of W, when you multiply it with something else, not necessarily you get something that integrates to 1 anymore, okay? So what we need to do is to properly normalize it. And the way we do it is to simply integrate the numerator, and this is P of Y given X, okay? So we ensure that the integral of the posterior is 1, okay? Simple enough. I guess this is fairly simple for everyone. If you don't follow, just raise your hand, okay? Right, so now the tedious exercise is as follows. There is this property which is quite famous in Bayesian inference, which is called conjugacy. So if your prior is Gaussian and your likelihood is Gaussian, well, it means that this is all quadratic forms inside the exp. So when you multiply to exp, you have quadratic forms that sum up. So this is going to be, again, a polynomial of order 2. Yeah? And guess what? Then the posterior is going to be Gaussian. Okay? So this is why people love Bayesian inference when everything is Gaussian, because everything is analytic. And of course, conjugacy is also between other pairs of distributions. But here, everything is Gaussian. Okay? So Gaussian prior, Gaussian posterior. So that means that what we can do is simply to multiply the prior and the likelihood. Okay? So first of all, the form that we will get for the posterior is going to be Gaussian. Okay, so we're going to have a mean and a covariance, mu and sigma. Okay, so I just expanded just to show you what you get in the end. And ignoring any normalization constants, what you get in the end is this quadratic form with W, and then this other quadratic form with W and mu. Okay, and now what you have to do is to just multiply the likelihood and the prior together and try to get something that looks like the prior, like the posterior. Okay, so this is the posterior. Okay, from the previous slide. And now what I'm doing here is to multiply likelihood and the prior. Okay, so it's a simple exercise. It's called completing the square. Okay, if you do it, then you end up. I'm going to skip the details. Okay, I'll just leave them in the slides so that you know I guess the slides will be available after the presentation. So this is for your own reference. Okay, so if you want to follow the steps, then what you get by matching the mean and the covariance, you get that. The covariance should look like this. Okay, so we have this form that looks very much like a least square. Okay, except that this is regularized now by the inverse covariance, and the mean is simply this other form here. Okay. Okay, so you see that the covariance doesn't depend on y, which is kind of interesting. Okay, and the mean instead depends on everything. Okay, it depends on y and x. Okay, so we said that the posterior must be Gaussian, and the covariance and the mean are as follows. Okay, and now because everything is Gaussian, you can also make predictions. And if you do a tedious exercise as before, so completing the square again, you can obtain this very cool expression I really love. You know, when I saw this first time, first few times I was studying Bayesian inference, I got really interested. This is, I integrate out parameters from the model. Okay, so I have this P of y star. P of y star, you can define it given x star, so a new x, okay, and w. And then you can weight this by the posterior. So you can multiply by P of w given everything else, so your posterior, and integrate out w. Okay? So this expression here is really cool. There are no parameters anymore. So this is parameter-free predictions. Okay? And it's not really parameter-free, it's that you're accounting for an infinite number of parameters that are compatible with the data when you make your predictions. And this is really beautiful because you see w disappear. Okay? Okay, sigma square is still there, but we can do something about it if you want. So because everything is Gaussian, even the predictions are going to be Gaussian, and we can get rid of the parameters, which is really cool. Okay? And again, you just complete the square, and it's super simple. Okay. Why did I tell you all this? Okay. Well, now we have the tools to move one step forward, which is let's now think that I don't only have the features. Okay. So I have some data, but I'm not happy with just the features. So if I just do linear regression, my decision functions, well, my regression functions are going to be hyperplanes. Okay. Maybe I want something else. I know that there is periodicity in my data, so maybe I want some sine, cosine. So can I do this? Well, it's fairly simple to do. You just transform your inputs using a phi function, phi1 to phi d, okay? And then you construct another matrix, which you call phi, and you replace, in your linear regression, you replace x with phi, okay? So now, the model is still a linear model because the parameters enter in the same way, okay, as before, you see? So instead of having, sorry, let me just scroll back. So instead of having the likelihood like this, okay, with xw, now I replace x with phi, okay? But w still appears in linear form. So if I put a Gaussian prior, the likelihood is going to be again Gaussian, and then the posterior is going to be Gaussian. So even though I can make the model fit nonlinear functions, the model, the Bayesian model, is still linear in W. Okay, this is really cool. So I can just replace phi whenever I saw x before, and I just write the same equations as before. So my covariance now is going to be the same as before, where I replaced x with phi, and now same for the mean. Okay. Predictions, the same. Okay, I just replace whenever I see x, I just put phi. Okay. But now this is the problem. How do we choose these basis functions? Okay, so do we want sine? Do we want cosine? Do we want x? Do we want log? Well, maybe we have a prior knowledge about this. Maybe we know that there is a seasonality in the temperature time series you have, and this is just going to be a sine or with the proper phase shift. But maybe you don't know. And now the harder problem. Imagine that you have 10 options for each feature. Okay, so imagine that you have 10 different kinds of functions you would like to put into this model. And now you have 10 features. Okay, so how many combinations you can think of this? Okay, so how many new features can you construct? You can apply, some of these 10 functions to some of these features, and some other don't. Or you have an exploding number of possibilities here. Okay, really huge numbers. So if you try to choose the basis functions yourself, you just need to craft a way to do this, yeah? And maybe this is not optimal. You would like to be able to know what are the best functions to apply to these features, right? But then this would be good because everything is analytic here, right? So if this linear regression is a solved problem. Everything is, comes out analytically. It's beautiful. So if I had a way to do this, then it would be great. But the only issue really is that if I want to apply these 10 functions to all these 10 dimensions, and I want to do all possible combinations of these things, you get something in the order of exponentially growing number of new features, which is okay. But the only problem is that you have to then invert a matrix which is going to be d by d, d being the number of features. And inverting these huge matrices can become very hard. Okay, so maybe this manual construction of adding sine, cosine of different features to your design matrix, it's not going to work. So can we use Bayesian inference to get a better way to do this? So the beauty of Gaussian processes is that you implicitly work with an infinite number of basis functions, okay? And you sort of learn a probabilistic combination of these. But a beautiful thing about this is that you never invert this infinite by infinite matrix, okay? Because if you get D to be infinite, now you will have this phi transpose phi inside the way to compute the covariance will be infinite by infinite, and you wouldn't be able to compute it. But so what I'm going to show you is that actually you don't really need to work with this infinite by infinite matrix, okay? So kind of the tricks that Ray presented yesterday. Even in Gaussian processes, even though the number of basis functions is infinite, well, the number of data they will have probably is going to be finite, okay? So then that means that you cannot go beyond that, okay? So in practice, then the number of parameters in this non-parametric model will grow as the number of data. You're not going to have more than that, okay? And I'm going to show you in a minute how to do this. So what I'm going to show you is that all the predictions with this Bayesian linear regression model can be done in a way that you can separate. So all the terms that come into play separate out this the dependency between the inputs. Okay. So if that's the case, then what I can do is to first map the data and then do Bayesian linear regression, or simply whenever I see this scalar product between phi transpose psi of x and psi of x prime, I just replace k. Okay, so I can work with either k or psi. Okay, and why is this useful? Well, if I work with psi, then what I'm doing is to map into large dimensional space, d-dimensional space, and then I have to do this inversion of the phi transpose phi of the covariance, yeah, to obtain the covariance. And this is going to cost me order d cube time, okay? Because inversions, well, you have to do Cholesky factorizations, and or even if you do Gauss-Jordan, which is what you shouldn't do, this is order d cube. And you need to store this D by D matrix. If you work with K instead, well, what you're interested in is just storing K for any pairs of training points, okay? And then, this is going to cost you n cubed time. I'll show you. You need to do something with this n by n matrix. And also you have to store it. So first thing you could say, well, if you're going to work with D that is greater than n, then probably you should think about working with K. But if your D is smaller than n, then probably you should think about using psi formulation. Okay? But actually, why we do this is not to make computations faster, but is to say, well, what if I could pick K so that psi is infinite? This would be really cool. Okay? And this is really the essence of what kernel machines try to do. So for those of you that have done, have seen SVMs, this is really the kernel trick. Okay? And I'm going to show you that even for Gaussian processes, this holds. Okay? So we can find a K such that psi is going to be infinite dimensional. Okay? And because the formulation of the model is either through the scalar products or this function K, so as long as I can compute this K between two inputs, I can choose a K so that this psi is infinite dimensional, and I don't ever need to work with anything infinite dimensional. Yeah? I can only work with this K and all the pairs of the inputs. Okay? And it's very simple to show that if you take this kernel, as we call it, K, okay, this function here, simple exp of the difference between, it looks like a Gaussian, okay? Again, everything is Gaussian. Then you can show that psi is infinite dimensional. And I have a proof of that in the slides. I'm going to show it to you in a minute. And there are other kernels satisfying this property, of course, but I'm going to show it to you in a second. So this is very simple, okay? And it took me a while for some reason to figure it out. People used to say, when I was working with SVMs, many years ago, I'm not going to tell you how many, people used to say, yeah, you do this thing, you map your points in this infinite dimensional space, you do your linear classifier there, you map back all the results into your original space. And I didn't really, I used to use these things like, software packages, and I thought, okay, this works. And I never really tried to understand why you would get an infinite dimensional mapping implicitly. So this is my explanation in 2 slides on how you derive this, okay? And hopefully this is going to be useful for you. So just to make things simple, let's use univariate inputs, okay? Because this is much simpler to show. So now my kernel is going to be k xy, is going to be exp of this quadratic form, okay? So I can separate out now exp of minus x squared half, exp of minus y squared half, and exp of xy. Okay. Now, let's only focus on the last term. You see that by just doing this expansion, already we separate out x from y in these 2 terms. But here, x and y, kind of, you cannot really separate them out, okay, because they appear inside the exp. But what if we do Taylor? So if we do Taylor, we obtain this Taylor expansion for the xy. And now, if I construct this psi function such that I normalize it by this exp of minus x squared half, and then I have this progression, which is the sort of, if you look at the series here, I'm thinking of an infinite dimensional vector where I have a 1, x squared, square root of 2 factorial, x cubed, and so on. Okay. Now, if I construct this infinite dimensional vector, it's simple to show that if you do psi transpose x, psi y, I obtain the series I showed you before, and therefore this. Okay. So this is a simple trick, simple way to show that you can find an explicit representation, actually, in this case, which is infinite dimensional for if you use a kernel that is Gaussian. Okay. Fantastic. So now we have a way to do this, and in order for me to show you that you can actually express now everything as only in terms of scalar products of psi, transpose psi, we need to use this ugly expression that I use a lot in my life. I used a lot in my life, and I can get to myself to remember. for some reason. And I have a nice picture later on for this, okay? And maybe it's going to help you. But so the idea is that whenever you have to do an inversion of matrices of this kind, you can replace the inversion with this expression, okay? And we're going to see, if we apply this consistently, we can show that actually predictions can be expressed only in terms of scalar products, okay? So if you look at the expression of covariance, I'm going to just go skim through this, okay? And then offline you can spend a bit of time and work it out if you want. But you see that we have this ugly inverse here and then another inverse, okay? So whenever you work with these Gaussian processes, unfortunately, you always have sums. Something is inverse inside and then there is an inverse outside. So this thing kind of helps out because imagine now you see that if this guy is inverse in your expression, then this inversion A appears only -1 here. So you can kill the -1. So this is kind of nice. So here you see that what we're going to do, we're going to say that A is equal to S in our expression so that whatever we get out of the application of Woodbury identity is going to kill the inverse here, okay? But if you just repeatedly apply this, you apply it once for the covariance and you obtain this ugly expression. But you see that already things start to change, yeah? So here you had this phi transpose phi. This was a matrix which was d by d. And now this becomes phi s phi transpose. So this is the other way around. So it's going to be n by n now, okay? So you turn an inversion of a d by d matrix into an inversion of a n by n matrix by doing this, okay? And remember that the mean and the covariance have this expression over here, okay? So and now you just plug in your rewriting of the sigma, okay? And you get this ugly expression here. And if you keep going, you also rewrite the variance like this. And now you arrive at this place, okay? And now here, this is what I'm saying. If I define psi to be S1/2 phi, okay, then I can replace all these terms by the corresponding k function, okay? So it's kind of tedious, okay, to do this manipulation of algebraic quantities, but in the end, you see that here, everything appears in the form of, phi s phi, okay? So I split S in half, if you like, and I create two sort of separate mappings, and one is going to be psi of x, and whenever we have this, for example, this is going to be psi x star, psi x star, yeah? And so these are the expressions that you get in the end. Okay, so the same you can do for the mean. I'm not going to show it to you, okay, but it's in the slide. And here you have to apply twice this Woodbury identity to show it, okay? And you get very ugly expressions like this. You have this identity minus h-1 plus identity things, But in any case, if you consistently apply this, even the mean can be rewritten in a way that only requires kernel evaluations, okay? Okay, so this was, whenever you see this proof here in the slides, it's something that requires a bit of work, okay? But in the end, what I'm trying to say is that, again, when you want to make a prediction with your model, then everything can be expressed with respect to scalar products, with respect to kernel functions, okay? So you don't need anything else. And I wanted to say something about this. Okay, so we choose, the other thing, important thing to notice is that now if you are interested in W, so the posterior over W, well now W lives in this infinite dimensional space. So we cannot really evaluate the posterior anymore because the covariance will be infinite by infinite, okay? But what I'm doing here is by, plugging this back into the predictions, this infinite by infinite stuff just disappears, okay? And everything is just expressed in terms of kernel, okay? All right, this was the ugly way, okay? But this is to show you the connection with Bayesian linear regression. And now there is a much neater way to express this, which is the function space view, which I like. And usually when I give talks, this is the way I motivate Gaussian processes and I introduce Gaussian processes. It's a bit more visual. And I think I also did this at Yandex in April. I presented it this way. So the way I think about this is, imagine you have a real line that is your index, okay? And then for each element in your index, you have a Gaussian random variable. Okay, so if you draw independently all these Gaussians, you get white noise. Okay, you're gonna get an infinite number of Gaussians, and they're all independent. So there's no structure, it looks like noise. And your covariance is gonna look like an infinite by infinite covariance, which is diagonal. Okay. Okay. Now consider again the Gaussian kernel. And you can play around, so you can start adding parameters, and of course, you can make it as flexible as you like. So imagine I put it here, okay, just for visualization purposes. Okay. So now imagine that what I do is to impose covariance between variables following this pattern. Okay. So I'm going to fix one of the variables, the one over here. Okay. And I'm going to say that the ones nearby are going to covary a lot with that. And then as I move away from that point, the random variables are allowed to do whatever they want. Okay? So now if I do this, and I draw, with fixing this point, what I get is something that looks like functions. Okay? And the reason, again, is that whatever is nearby in space, okay, all the random variables around the one I fixed will have to covary with, will have covariance 1 with the one I fixed, or close to 1. So whenever you draw around that point, the variables cannot move around as much as they want. They will have to have a similar value. Okay? But as they move away from that, then they're allowed to do whatever they want. Okay? And this, as a result, you get something that looks like this. Okay? If I draw a lot of these things, all these things look like Gaussian, look like functions. Okay? Okay, now I can also unfix the point, the original point, and make that random too. And what I get is something that looks really like a prior of a functions. Okay? So when I draw from these things, I get functions. And now the covariance, though, is still infinite by infinite, but this is going to be full now, because the covariance is going to express the covariance between two random variables, right? And really, the covariance of this point with this point is almost 0. Okay, well, it's Gaussian, so it's never going to be really 0, right? And numerically, you can think that at some point it's negligible. But really, you're going to get a lot of non-zero elements in this big matrix, right? So now here's the challenge, right? So I'm expressing something in a way that is infinite by infinite and dense. Okay, so this looks really bad. So here I'm playing around now with parameters. I showed you before the Gaussian kernel. If you put parameters, you can start making these functions, look smoother, more, frequent. You can increase the, amplitude if you like. Okay. So here it's from smoother to more rugged, and here it's from low amplitude to bigger, larger amplitude. But now the beautiful property of Gaussians is the following. So if I observe data at certain points, and I want to characterize the covariance of all the random variables at those points, I really don't need anything else. Because the marginal of a Gaussian, a multivariate Gaussian, is again Gaussian, and you only need to consider the variables you care about. So if I have x1 to x infinity, but I only care about x1 to x3, the marginal likelihood will have Gaussian distribution, and the covariance will require selecting the corresponding variables. And that's it. Okay? So the only thing I need is to select the n variables I care about. Because all the others can do whatever they want, but they're not going to affect the marginal. Okay? So this is a good property. And again, now the only thing we need to do is to apply the laws of algebra, right? And we know that then the variable f that we call latent variable, okay, the function at the random variable corresponding to each input is going to be jointly Gaussian, and it's going to be jointly Gaussian with covariance k. Okay, and now what you can do is to start playing around and say, okay, what if I have another test x star? Okay, I want to test, I want to look at the distribution of f star. Well, what you do is to just augment the covariance by 1 and look at the properties of conditional Gaussians, yeah? And what you get is this form, okay? And I believe something is missing here. There's an F missing there. Okay, apologies. And then you get something that starts looking very much like what I showed you before for the weight space view. Okay, so if I just keep it short, and again, we do the same as before. We say, okay, we have these latent functions that we don't observe. Okay, what we observe is y, and we assume that y is a noisy realization of f. Okay, so as before, we have a likelihood that factorizes across the observations, and we're going to have Gaussian centered on fi with variance sigma square. So now, because the Gaussian process is a multivariate Gaussian, okay, and the likelihood is Gaussian, guess what? Then we can integrate out f. And so we can do this p of y given x, if you like. So we can integrate out and get p of y, by doing p of y given f times p of f given x, integrating out f, right? And then in the end, what we get is that p of y given x is going to be Gaussian with the k original covariance plus some diagonal noise. Okay, so now we can do all the exercises as before, but I'm going to skip this slide, and I'm going to just go directly to this, and we can derive the same as before. If you do a bit of manipulation, then you can derive the predictions p of y star given y, x star, and x. So again, no parameters anymore, no f anymore. You get exactly the same expressions as before. Okay, so by taking an alternative view, okay, so by just looking at what these variables are, multivariate Gaussian, then you can just use the rules of conditioning of multivariate Gaussians and marginalization to get exactly the same expression. Okay, and the picture. Okay, so if you do it, then you get this beautiful picture. Okay, so now what I'm showing here is the posterior distribution over f. Okay, so I'm showing you all the functions that are somehow compatible with the data we have. Okay, so I'm drawing from, if you like, p of f star given data. Okay, everybody happy, more or less? Questions? I think it just takes a bit of time to just go through again the nitty-gritty details, right? Because intuitively, this is all it is. Okay, multivariate Gaussian. If you look at the infinite, you want to only n. You want to look at only n out of infinity. Then you only need to consider this n by n covariance matrix. And then if you want to make predictions, you just augment the number of variables to add this x star variable. Okay, so we're going to have n plus 1 times n plus 1. And all you need to do is to apply the rules of conditioning of Gaussians. Okay, and again, you go to Wikipedia or Bishop's book, whatever, and you're going to find the rules of conditioning. Okay, and by applying these rules, okay, this is the kind of pictures you get. Okay. Okay, so clearly now, I mean, we have choice on how do we choose k. Okay, and just for the simplicity, I showed you this Gaussian kernel, but of course there has been a lot of work on engineering good kernels for different problems. But just for the sake of presentation, think again about this Gaussian kernel. Okay, so and just parameterize the kernel so that you add these parameters alpha and beta. Okay, and remember that we also have the noise parameter sigma square. So if we are in regression, okay, so we want to figure out what is the variance of the noise. So define theta, now green from now on, as alpha, beta, and sigma square. Okay, so how do we tune them? Okay, so these are parameters of my model. So this is a non-parametric model. Gaussian processes are non-parametric because the capacity grows. So the more x you give me, the more this covariance matrix grows. But now, actually, we have parameters. We have these hyper parameters that control the smoothness of the functions and so on. So when we have a problem, we want to find the right, not only the right functions that pass through the data, but also what is the degree of smoothness of these functions, what is the amplitude, and so on, and also the noise, yeah, on the observations. The beauty of GPs is that because it's a probabilistic kernel machine, then we can write the likelihood, so-called marginal likelihood, because we integrate out f. So we have access directly to p of y given x and theta. Okay, so this is just like any other model. You have probability of observations given parameters. Okay, so if you want to do maximum likelihood, what you do is just optimize p of y given x and theta with respect to theta. That's it. So it's much
simpler than fancy other models. Okay.
So
but
both your students, this is one of the classical examples of Bayesian model selection, and this is what we'll study in a week and a half.
Okay. So here you have a lot of options, right? So theta, if you are, you've been probabilistic and Bayesian so far because f is a, infinite number of functions and so on and so forth. You integrate out and everything is Bayesian. But once you get to this point, you can think, well, I just optimize the theta parameters. I don't care about anything else. If you're a bit more Bayesian, like me, maybe you want to also do Bayesian inference on theta. Yeah? But you still kind of need, whatever you do, you always need to work with the likelihood. Okay? But this is a Gaussian, multivariate Gaussian. What is the log likelihood? We know, right? So it's just the log of a multivariate Gaussian density. Okay? So we have the log determinant of the covariance and then the quadratic form here. Okay? So if you just want to optimize, what you can do is to just say, call your favorite routine, optimization routine, and just give the objective function. And maybe if you want to help the optimizer, just give the gradients. Okay? And the gradients, they look very nasty, but actually it's not so bad. So the derivative of the log determinant becomes this trace, okay, with the inverse times the derivative of the matrix. And then this quadratic form becomes an uglier quadratic form. Okay? But again, if you look closely enough, you see that you have this k minus 1y that kind of appears here, here. And so you can kind of reuse a lot of the computations you use to compute the actual marginal likelihood. Okay? So this is 3 lines of code to code up. Okay? And if you look at Rasmussen's and Williams' book, you actually have a lot of good details on how to implement these models in a neat way. So whenever you want to do inverse of a matrix times a vector, you never really do that. You just do Cholesky decompositions first, and then you do back-forward substitution. Show of hands, how many people know Cholesky algorithm or have heard of it? Some, okay. So if you want to solve a linear system.
And how many people do know how to differentiate matrix determinant with respect to parameter?
Okay, so I'll tell you about this as well. So what I'm telling you here is, so remember the k is a function of the inputs, okay, because it's k, it's got pairs of inputs, but also it depends on parameters, theta, alpha, beta, and sigma square, right? So when you want to take the derivative of a matrix with respect to parameters, what you have to do is to differentiate every single element of the matrix with respect to the parameters. So very simply, if I take the derivative of this matrix with respect to sigma square, I'm going to get the identity. Plain and simple, because only the diagonal elements have plus sigma square I. Yeah? Everything else doesn't. So the derivative of ky with respect to sigma square is just going to be the identity. Okay? Then for k, it's a bit harder because the parameters, for alpha and beta, the parameters enter k. So you have to, just element by element do this. Yeah. Okay, and Cholesky decomposition. So if you want to solve linear systems, the way I was taught how to solve linear systems when I was a physics undergrad was to do Gauss-Jordan elimination. Okay, so you take your matrix, take your solution, start shuffling around rows of your matrix, multiply, and so on. Turns out that there are better ways, numerically safer ways to do this. So one way is to decompose the matrix to be L transpose, where L is a lower triangular matrix. Okay, so you transform ky into something which is the product of a lower triangular matrix and an upper triangular matrix. Okay, with the lower and upper triangular, I mean that the non-zero element are in the lower triangular part of the matrix and zeros otherwise. Okay, so if you do this, it turns out that it's numerically stable to do inversions, numerically better condition to do inversions. And also the log determinant comes out to be very neat because the determinant of a product of LL transpose is going to be the product of the determinants. And the determinant of a triangular matrix, it's super simple. It's just the product of the diagonals. yeah, because all the rest, the upper triangular part is 0. So if you think of it for a minute on the definition of the determinant, because there are so many zeros, it turns out that the determinant is just going to be the product of the diagonal elements. Okay? So once you've solved the Cholesky algorithm, the Cholesky decomposition, doing this log determinant is n operations, just summing, products of these diagonal elements. And actually solving linear systems, so solving this ky minus 1y also is simple. It costs only order n square operations. Okay? There are algorithms called back and forth substitutions to do this. Okay? But they're very simple. Okay? Great. Now, what are the challenges? Okay, so I think I'm doing well with time. Good. So far, as I said, take Rasmussen's book if you like this sort of topic. If you have never done it, implement these 3 lines of code for Gaussian processes. And you can do all these cool pictures, with all these error bars, and beautiful. But now what are the challenges? Well, everything works if it's Gaussian. Yeah? So if the likelihood is Gaussian, the prior is Gaussian process, so it's Gaussian, everything is Gaussian. But now if it's non-Gaussian, what happens? Well, do you guys know about generalized linear models? Have you heard of it? So you have a linear model with a likelihood which is non-Gaussian, then you have to do something if you want to be Bayesian. Yeah? Because, again, you get the prior on the parameters that is Gaussian, likelihood that is non-Gaussian. Okay? So imagine that you have counts. You're trying to do regression on counts. Okay? So you have a map where points, observations are how many cases of a certain disease happen in a certain place, so epidemiological studies. And you want to do some regression, but the data is not continuous, it's counts. How do you do it? If you have a classification problem, imagine a famous MNIST, okay? Well, the likelihood is multinomial. So how do you do non-Gaussian likelihoods? Because now the prior is Gaussian, but the likelihood is not. And also now I have this n by n matrix that I have to store, okay? And I have to factorize. And now if someone comes to me and says, okay, this is this 15 million images to do classification on, how do I store a 15 million by 15 million matrix? And how do I factorize it? Okay? So as of today, I don't think we can go beyond, with a very big computer on a single machine, I think we can go with 256 gigabytes, maybe 500 gigabytes of RAM. We can go up to a few tens of thousands. Okay, maybe also we can push it to 100,000, maybe. But that's it. Forget about a million. Okay. So how do we do it? So I'm going to try to illustrate the challenges now. I'm going to tell you what people have done briefly. And then I'm going to show you the last part of the talk where people are trying to to jointly tackle these two problems. Okay. So, as I said before, we have a marginal likelihood which is of this form. So we have the Gaussian process prior, which is Gaussian here, P of f, given x and theta, and then we have the likelihood. And now imagine that the likelihood is Bernoulli. We have we squash the function using a sigmoid maybe, and then we do Bernoulli likelihood, or we do softmax. Okay, so f is multivariate. We have multiple functions, all coming from a Gaussian process. We do a softmax, and then we use this as a multinomial likelihood for class labels in a multi-class classification problem. So what do we do? Well, let's approximate it with a Gaussian, right? So this is the big thing that people have done in machine learning for many years. So it kind of all started with, in machine learning at least, because whenever I say things, then I gave a talk in Edinburgh a few months ago, and last year. And Chris Williams was in the audience, and whenever I said something, people have done this in 2000 something, he said, there was a guy that did this in physics in 60s, okay. And so a lot of these results probably appear in some other literature, okay? But I'm trying to give you the machine learning view of this, okay? So people have started thinking, well, with this, if you think about classification, what you do, in binary classification, you take your latent functions and then you squash them using a sigmoid function. Okay, and then you use this as a probability of class labels. This is what people do also in generalized linear models. So now if you think about it, you can start thinking, well, the sigmoid has this particular shape. It's the logistic function. Okay, So you can start thinking, well, I can construct a lower bound which is Gaussian, which is pretty cool, and an upper bound that has another form, so that I have two bounds that I can plug into my estimate of the marginal likelihood, and then get something which is all Gaussian again. Okay, this was early work by that you can find in Gibbs' thesis as well, and also in this IEEE TNN paper. Back in 1998, actually, Chris Williams and David Barber in PAMI. This was 98, yes. They did the Laplace approximation even for multi-class classification. So Laplace approximation works as follows. So you're multiplying now two functions. One is the Gaussian process prior and the likelihood, and they're not Gaussian, okay? So one is Gaussian and the other one is softmax. So what you can do is to say, well, let's find the mode of this product, and then let's try to find the best Gaussian that approximates this product of these two functions. Okay, so this is called Laplace approximation, and it's motivated by, again, Taylor expansion. So if you think about the way you should approximate any distribution, okay, that you don't know how to characterize analytically, well, if you just find the mode of this and then you try to find the curvature that matches the curvature, well, you find you set the covariance of your Gaussian approximation to match the curvature of the function, then you get something which is reasonable, yeah? And the curvature is expressed by the Hessian, okay? So you compute the Hessian, and it turns out that if you take minus the Hessian inverse, that's going to be the best covariance you can find to approximate your function, okay? So this is called Laplace approximation. It goes back many years back in other contexts. Well, yeah. But also in other contexts of statistical models, there is this, I can't remember the reference exactly, but Tierney and Kedan in 19-something, that they proposed this for statistics in general. This was the other big thing in early 2000, expectation propagation. So we're approximating with a Gaussian, right? But the Gaussian now has the problem that it only finds one mode and then tries to find the curvature there, which is kind of good, okay? But the posterior for most of these Gaussian processes of, the product of your likelihood and the prior, a Gaussian process prior, is usually kind of unimodal for many likelihoods. So it's kind of nicely behaved. So this Laplace approximation is not such a bad idea. But the posteriors, a lot of times, look very skewed, okay? So then just finding the mode and approximating there, it's not going to be too good, okay? So people have thought maybe we could find out better ways to approximate. So fortunately, yesterday we had Elias' talk on divergences, and what people do is to just say, well, let's minimize the KL divergence between the distribution I'm trying to approximate and the Gaussian approximation. So it turns out that now you can play around, and you're going to place your Gaussian not at the mode, but at the mean of your distribution, which is going to help if posteriors are skewed and so on. Generally, I think it's quite widely accepted that EP is a better approximation than Laplace approximation. But actually, I have friends that told me the opposite. But I wouldn't swear on that. But anyways, so they have pros and cons. And also, then if you take the KL divergence the other way around, then you can get other methods, which are called variational-based methods. So depending on how you take the KL divergence, then you can get different kinds of approximations, okay? And these appear in a nice paper by Nikic and Rasmussen, which is really a survey paper on approximate methods for that, and also variational-based, like mean field approximations and so on, by Oppen and Archambault. Okay, so this was the first decade of 2000, okay? And of course, there has been, if you really don't want to make approximations, what do you do? Well, then you can't. You have to do some approximations. But if you do stochastic approximations like Markov chain Monte Carlo, then eventually you know that asymptotically you're going to find something which is unbiased. Okay. So there has been some work on this. There was Radford Neal that has done some work on this. But I would say that the Murray and Adams paper in 2010 NIPS really improved massively on that, and we also improved on these approaches later 2014. Okay, this is just to say that this is all the kind of options you have, right? Okay, right now, but what if now let's go back to the case where everything is safe, like this Gaussian. And now, even then, as I said, you have this huge matrix that you have to factorize and store. So, and as I said, if you do this Cholesky algorithm, it's going to cost you order n cube order n cube operations that you have to invest to really factorize the matrix. You also need to store the matrix. So these days we're working on distributed versions of Cholesky with some students. And so we're trying to chunk up the matrix. You give me 1 million data points, I try to chunk it up and store it in different machines. And then there is a horrendous communication process that tries to coordinate this Cholesky in distributed. It's a pain. And you really need order n square. You have to store n by n numbers. So very easily you can use terabytes of data to store everything. Okay. So can we do better than that? And this is my beautiful visualization of Woodbury identity. Okay? So imagine that we have this K, as before, we have a dense matrix plus the diagonal. Yeah? And imagine now we can find a low-rank approximation to that. So imagine that we can express this matrix here as the product of a skinny matrix, as we call it, okay? Which is going to be n by less than n, then a small less than n by less than n matrix, and then another fat matrix like that. Okay? So if we can do that, then if we apply Woodbury, we get this expression, okay, which I really like because it shows me that my inversion here, so remember that with this matrix we have to do determinant and we have to invert it. Now, what I have to invert is something which is of the size of this block here, m by m, okay, because this guy here is going to be m by m, where m is less than n, okay. This is going to be the sum of two m by m matrices. And then I have to take the inverse of a smaller matrix. So a lot of the work, well, I would say, well, more than 90% of the work that has been done on scalable Gaussian processes do this. Okay? This is all it is. You take a low-rank approximation. Okay? Okay? So there are different ways to do this. One is to say, let's take a number of points, or maybe let's throw away n minus m points. And let's just use m out of n. Okay? This is called the so-called subset of data, okay, which is the first thing you can do. You give me 1 million data points, thank you, but I'm going to use only 20,000. Okay? And then I'm going to try to express the full process on the 1 million data points by using this subset of 20,000 points. Okay? Okay, this was studied in various papers. And then this idea of the pseudo inputs. Okay, so now let's start thinking of new points that you create out of the blue. And you say, I'm going to express the full process, f, on my 1 million data points by using a subset, well, a set of new variables. Okay? And now if you express this, it's nice because what you can do is to start saying, well, maybe the position of my inputs can change. Okay? So I'm given 1 million inputs with associated labels. What I can do is to say, well, now I have 10,000 new inputs with associated labels, with associated function, latent function. And what I can do is to try to position these new inputs optimally somehow. So what they did here in this works, they try to do this exactly. Okay, so they have a formulation that allows them to optimize the position of the points. So then a lot of these ideas on sparse Gaussian processes have been unified in a beautiful paper by Quignonero, Candela, and Rasmussen in JMLR 2005, which is called the Unifying View of Sparse Methods for Gaussian Processes, something like that. And then in 2009, this is really what created the revolution for modern GPs. It's Tizia's work in AI stats on finding a better way from the variational perspective on how to express the approximation to the full process given a set of new variables. Okay? So basically you get the same as before with an extra regularization term that gives a much better performance and also allows for better placement of the inputs. Okay. And I should also mention that, so all these works here are low rank with pseudo inputs. So you assume that in space you create either you create new points with associated variables, or you just select some from the original data points. But now this is an approximation by taking a low rank, if you like, in space. Okay? What you can do is to apply some Fourier analysis to do some clever tricks to actually do the same in frequency space. So for those of you, I hope, well, I guess most of you have seen Fourier transforms. Yeah? Raise of hands, please. Okay. So actually, if you just do harmonic analysis, it's quite simple to show that you can expand your kernel pretty much the same way I showed you before with Taylor. You can do any other basis really, right? So you can do Fourier basis. Okay. And by doing that, you can show that you can construct this sine and cosine in the case of a Gaussian. Yeah. You get this sine and, well, complex, sine and cosine. Yeah. It's a cosine plus complex sine, yeah? And that's it. And these can be thought of as just basis functions, yeah? You truncate at some point, and this is going to be your low-rank approximation. So this idea was super successful in kernel methods. This is Rahimi and Recht 2008. And this was later adapted to Gaussian processes in Lazzaro Gradiglia and others in GMLR 2010. There are other interesting approaches that I would like to mention. So the idea is that, well, instead of having now a set of inputs that you place in space and so on, why don't we just lay a grid in space? Well, if we do that, then there are going to be a lot of inversions of matrices that are based on evaluation of the kernel at certain points. So if at regular points. And it turns out that these matrices have particular structures, Toeplitz, circulant, and so on. And actually inverting these matrices is super fast. Okay? So there have been a number of works by Andrew Wilson, that is also author in this paper, that really try to do this, to exploit this idea of structured inducing points, if you like. Okay? And they scale quite well because they scale linearly with n. Okay? But there is still the problem of large dimensionality, of course, because if you start now, increasing the dimensionality, well, laying a grid on in the dimensions starts to become, exponentially, more difficult as you increase d. Yeah, and I believe that a lot of these approaches are understudied for and underused for a lot of applications. So if you have a one-dimensional problem, you can just do a lot of things pretty much in order n these days, okay? Linear time. When you start increasing the dimensionality, things start to be a bit more complex. So in this work, they try to work with different models on univariate single features and then combine at the end. But they get super scalable GPs out of this. And I would like to make some advertisement, of course, of my work because I'm here, okay? And I was really excited when we did this because we improved the scalability of GPs the way we implement them now from order n cubed to order n square, okay? So instead of having this Cholesky decomposition now, we don't do this anymore. We do something else that allows us to reduce by an order n, if you like, from n cubed to n square. And also, we don't need to store K anymore, this big covariance matrix. So we did this at ICML 2015 and 16 in various forms. I think, okay, I can give you just the gist of the idea, right? So remember that this is the marginal likelihood in GP regression, okay? And this is the gradients, okay? What you can do is to rewrite the trace. So here you still have linear systems, okay, which is fine. But here you have a trace term, which is kind of nasty because no matter how you look at it, you have to spend order n cube operations. So if you first, you can invert this and then multiply. But if you invert, then it's going to cost you n cube. And then when you multiply by another matrix, well, the trace of a product actually is order n square, not n cube, because you just take element-wise product of the matrices and you sum everything, okay? So you could do first inversion and then it costs you n cube, and then everything is n squared. Or you can just do Cholesky, which costs you n cube, and then you back substitute, and then you take the trace. No matter how you look at it, it's n cube. So with this trick, which is the stochastic estimate of the trace, we can actually bypass the need to do these n cube operations by doing the following. So we just look at the trace term again. We make an identity matrix appear. So we say identity is here, okay? And now we say that we have vectors such that the covariance is the identity, okay? So that the expectation of R transpose is the identity. And now, because expectation and trace commute, I can put the expectation outside. And now the elements in the trace, you can make them circulate like this, okay? So I put R transpose, which is on the right most element, I put it at the beginning. So what I'm writing here is that the trace of this product becomes the expectation of a scalar, which is computed like this, okay? So in practice now, if I sample from R, if I sample these R vectors that have covariance identity, which is standard normals, if you like, then I can get an unbiased estimate of the trace term, okay? And unbiased estimates of parts of this gradient we like, because then we can use stochastic gradient optimization, yeah? So I just sample a bunch of these R vectors, and I compute these things. And if I look at this expression now, all I need to do is to solve linear systems, nothing else, okay? So this is a linear system, this is a linear system, and this is a linear system. Everything else is something that we can compute at order n squared at most. In linear systems, we can solve using conjugate gradient. So for those of you that don't know, there is iterative procedures to get the solutions to these systems, which only requires matrix vector products. The only thing I need to do is to be able to do matrix vector products. And for these, I don't need to store k, okay? And I can go super fast if you give me 10 GPUs. I can do this, massively parallel way, so I can go super fast, okay? But still, this is order n squared, okay? And then I can plug this into stochastic gradient optimizer, and this is going to work. So this is something I wanted to show you just as a teaser. As I said, put it there, teaser. So these are various approximations, okay? So variational, this is, I think it's Titius 2009. These are various subset of regressor approaches. And this is the Cholesky decomposition, okay? So what I'm showing here is the error versus time. You can see that sort of approximate methods are faster at obtaining some values of error, but then they plateau, okay? So it seems like you really need to use all the data. So this Cholesky conjugate gradient, the precondition conjugate gradient, use all the data. Yeah? So you can reach better error rates if you don't throw away information. Yeah? So this was the kind of motivation to do this. And here we show that the conjugate gradient can be faster than Cholesky, okay? But in some cases, if you precondition your system, so for those of you that don't know, it's a way to, so this conjugate gradient algorithm is numerically not super stable if your matrices are not well conditioned. So if you precondition the system by using some tricks, then you can go even faster, okay? This was a 1-minute teaser, okay? Just to say that in a lot of these cases, you don't know what the number of these pseudo inputs should be, right? So if you can use all the data, it seems like in most problems we've seen, you really need, almost all the data to do a good job, okay? But now I would like to draw your attention to what modern GP's work is doing, which is trying to tackle both problems, non-Gaussian likelihoods and scalability. And how do we do it? Well, it was a bitter lesson to learn that, deep nets are conquering the world, right? So maybe we can learn from this, okay? And why do they conquer the world? Well, did they conquer the world? Well, they can do mini batch based learning. So every time you want to update your model, you just need to give a batch of points to your model, and it's going to update. Well, for Gaussian processes, this is pretty hard. Remember, we have this n by n covariance. If I just look at the slice of the covariance, if I select a bunch of points, if I just look at the subset of this matrix, I'm not going to capture the whole covariance between points. So I cannot really do mini batch. How do we do this? Then deep nets, we can now with TensorFlow, just can do everything in GPUs very easily. You don't need to code pretty much anything anymore. Distributed computing, we're working on this for other models. I don't think it's still plug and play, TensorFlow distributed. I don't know if you have any experience on that, but there's still work to do, I think. But in principle, they can exploit, distributed computing. Asynchronous SGD, you send your batches to multiple machines, they do their updates, they get, there is coordination to update your model. Another big thing is automatic differentiation. I spent most of my life, taking derivatives. And now, we can do automatic differentiation. Why not? It's a tedious exercise, right? So derivatives, there is no mystery. It's just application of rules. So smart people have thought, well, we should probably make this available as a commodity now. And then, of course, you can really do a good job if you exploit the structure of your problem. If you're working with images, you should use convolutional layers. You should use convolutional representations of your problem. Yeah. So if you look at the leaderboard of MNIST and CIFAR10, there is, I think in CIFAR10, I think one of the top results, doesn't even have anything else than just convolutional layers. Okay? So that's the key, right? When people talk about deep learning, they should say, well, convolutional learning is a big thing, right? So, and I would say that only as we speak, we're working on these things for Gaussian processes. Okay, so I'm going to give you a few examples. So this was my animation, okay? This was a stochastic gradient optimization, right? So you have an unbiased estimate of your gradient. If you follow that, so whenever you interrogate your routine, you get a noisy estimate of your gradient. Well, eventually, you know that you're going to converge to local mode. And I'm pretty sure that this is the first reference to this, okay? Robbins and Monroe, 1951, okay? So a lot of people have taken this idea of mini batch. So what you do is to be able to express your objective function as a sum of things. And then what you do is to just select m out of n terms in your sum. And that's it. And then you plug it into stochastic gradient optimization, and it's going to work. So a lot of these works I'm going to mention now, they approximate the Gaussian processes in a way that you're able to really write your objective function as a sum that you can then use mini batch training. So there is this extension of expectation propagation to be scalable in Bui and others, ICML 2016. With inducing points methods, James, he's the guy, James Hensman. He did this Gaussian process for big data, okay, in 2013. And it's really the 2009 Titius paper with a realization that you can actually write the objective function as a sum, and then you can split it up. We did some extension of that for some MCMC sampling for that later on. And then this is the other one. So this was inducing points, and then people like me and Yarin Gal at Cambridge, we worked on ways to do random feature approximations, so this other low-rank approximation, if you like, and we did it at scale, okay? So we are able to write an objective function, which is, we use variational inference in that case, that is really, amenable to automatic differentiation, GPU computing, distributed computing, and we can do mini batch, okay? So just to give you a teaser, so here we have a bunch of examples. So here we're looking at, I don't like this example because it's going to take me a while to explain, and we don't have much time. Yeah, let's skip that. But in any case, we're very good, okay? So we are red and orange, okay? And the competitor is the GPEP, okay? And DNN are deep nets, and this is variational GP. We can get good results, scalable. This is only 15,000 data points. And just to give you a teaser, so now not only we can work with any likelihoods, we can also make the models deep, okay? Because if you think about it, a deep model, as I'm going to explain it to you now, you can think of this as a hierarchical GP, right? So your likelihood is another, is a likelihood on the observation passed through a GP, if you like. And you can have as many GPs as you want. So what does it mean to have a deep GP? Well, imagine you have a Gaussian process, some process, a stochastic process on the left, some other stochastic process on the right. And in deep nets, what do? They compose functions. When you have different layers, the only thing you're doing is composing functions. Can we compose processes? Of course we can. So if we give the one process as the input to another process, then we get pictures like this. Okay, so you see that these are kind of smooth at the top, and when you start composing, things start to become a bit more interesting, and also the uncertainty starts to be all funky and so on. And this is what I really like. So we could train our deep Gaussian process on 5 million observations, okay? And with different depths of this deep Gaussian process, so we could go up to, in this case, only 30 layers, up to 30 layers, okay? And we could do model selection. So because everything is probabilistic, we can show that, this is the model selection would tell us that 10 layers would be the best architecture, if you like. And this is in line with the results that we get on test performance. Okay, this is just to say, this is some competitor deep kernel learning by Wilson and others. Just to say that, maybe if you do a Bayesian deep net, also you can do some model selection, okay? But we have ways now to really push these models to go, and this was run on a single machine, not even, in distributed mode, okay? So we could run 5 million observations in no time. Okay. This was, again, a teaser, okay? Just a bit of advertisement. So what are interesting topics now? So I would like to conclude now my presentation by giving you a bit of, directions where people are looking at now these days. So this 1998 paper by Jones and others is the classic reference for Bayesian optimization. There is a lot of activity now, because if you can do good quantification of uncertainty somehow, then you can do better Bayesian optimization. Yeah. And for those of you that don't know what Bayesian optimization is imagine that you have a function that is really expensive to evaluate, or maybe not so expensive, but still painfully expensive. And what you can do is to interpolate using your Gaussian process and use the uncertainty to try to predict where is the minimum of your function. Okay. So then this is all started with this paper in 1998, and there is a lot of activities on this, and so be able to scale and do good quantification of uncertainty is definitely something that will help Bayesian optimization. We're working these days a lot on also showing that we can do unsupervised learning. So there was this paper by Neil Lawrence in 2004, the Gaussian process latent variable model. So imagine now that you have inputs that are stochastic, and then you pass them through Gaussian processes and you obtain some modeling of your data. Okay, so this is more in line with what Ilya presented yesterday, I think. So you can think of autoencoders with the Gaussian processes and so on, and also generative models. Okay, deep Gaussian processes I talked about. Okay, so stacking multiple GPs. So still, I think we made a massive improvement on state of the art with this work. So we can really train these deep Gaussian processes at scale now. Compared to the competition, we really improved massively what we could do. But still, I think there is room for improvement. So better variational inference, better random feature approximation. We're working on structured approximation. So fast food, for those of you that have seen this. For kernel machines, we can use all this fast structured approximation to go faster in larger dimensions. And this is quite interesting. A lot of people have seemed to be thinking about, well, why can't we just put these convolutional layers inside GPs, right? And we're working on this. Rasmussen, a student, and Rasmussen and James Hensman have just got a NIPS paper on this called convolutional Gaussian processes. And we have something coming out very soon on this too, which probably is going to be a slightly different angle. But there are also these kind of deep kernel learning papers by Wilson's group. And so we are now, you see the dates, we're only recently we're starting looking into, really enhancing the capacity of our models by also looking at structured like images and so on. So exploiting the spatial structure of images, for example, by using convolutional layers. So this is, I think, another interesting topic that we have Novi here, that is co-author of this paper, ASTAT 2017, on structured output. So when your output is not just simple, but you have chains, so, you have trees, for example, as the output. How do we do this? Okay, so there is work on this, and there is a lot of things going on, and this is one of the latest things I've been working on. I think it's really cool. I'm really excited about this. So there is a new movement called probabilistic numerics. This is Oxford mainly, Warwick, and Tübingen, Filippone. So the idea is that when you have something which is really expensive to compute, so imagine computing the determinant of a big matrix. Why don't we? Well, one way to look at the problem is to say, well, this is something I cannot evaluate because it's going to take me 1 million years to evaluate this quantity. Okay, so why don't we try to use this to think of this as an estimation problem? So I'm trying to find an estimate for this quantity that I cannot compute by looking at some evidence. So the idea here, what we did was to say, estimate the log determinant of a big matrix by just looking at matrix vector products. Okay, so take the matrix, multiply it by some vectors. You're going to have a prior on your determinant. You can get some bounds which are more or less loose for your for your log determinant, and then you use the evidence from matrix vector products to narrow down the values of the log determinant. And now you're going to have log determinant is going to be uncertain. Okay, and now we have uncertainty on this. Then we can maybe propagate forward into predictions. Okay, because we have uncertainty on the objective function, then it's expected that we're going to have some uncertainty on the predictions as well. Okay, so it's somehow working on a budget, if you like. Okay.
Right, so why I'm calling it probabilistic numerics? This is exactly Bayesian numerics.
There is, I didn't call it that, right? So there is a lot of discussion about why did he call it probabilistic numerics, and if it adds anything to what was already known in the past. So there is a bit of debate on that, but.
The Mackay was playing with approximating determinants back in the mid-90s, or late 90s or something.
Yeah.
The same.
Yeah, no, definitely. I mean, I'm sure this is not. The way we're doing it, I think it's pretty interesting because we combine a lot of ideas from Bayesian quadrature to, trying to put a Gaussian process on the eigenvalues of these matrices and try to do, it's fairly complicated, but it's quite interesting. I'm quite excited about this, and there's going to be a follow-up quite soon. So I'm funded by my institution, EURECOM, but I got this grant for, it's a chair, okay, of computational statistics from the AXA Research Fund. And I need to thank them, every time I give a talk. So, and it's a 7 years scholarship. There's going to be PhD scholarships, all year round. I have money to appoint PhD students, and it's always hard to attract good students. So if you are interested in the topic, please apply. Even unsolicited applications are welcome. And pretty much that's what I wanted to say, and it's 1 hour and a half. Thank you.
Let us thank the speaker.